The first topic we'll take up under, or aside from the common ion effect, an application of the common ion effect is the idea of buffered solutions. Buffers are solutions that resist changes in pH when either an acid or a base is added. A buffer is formed when you combine a weak acid and a salt of its conjugate base. So for instance, weak acid, we could use, say, HCN as a weak acid, and a salt of the conjugate base. So the conjugate base would be Cn minus, so a salt of that might be sodium cyanide, NaCN. So when you dissolve the sodium cyanide in solution, you basically get that conjugate base, the Cn minus. Or alternatively, you could have a weak base and a salt of its conjugate acid. So for instance, if you had NH3 as the weak base and the conjugate acid would be NH4 plus, so we could use ammonium chloride. So ammonium and ammonium chloride could also act as a buffered solution. The idea of keeping the pH somewhat stable comes from the fact that if you have both the acid and the conjugate base, if you add either acid or base to solution, you have something there to neutralize it. So in this first pictorial here, we have base being added to the buffer. And so the buffer is this part here in the middle. In this case, the combination is the acid hydrogen fluoride and the conjugate base fluoride ion. So if you add base to this, what it's going to do is it's going to react with the acid that's present, forming water, and the fluoride ion, which of course are neutral. Of course, the fluoride is itself a conjugate base. But you're not going to get a huge drastic change in the amount of acid and base. So it'll help stabilize, or we say buffer, the solution. With the addition of acid, the acid's going to react with the conjugate base, in this case the fluoride ion. And again, you see that from the pictorial that the HF concentration is going to go up a little bit, the F minus concentration is going to go down a little bit, but we've neutralized that hydrogen ion that we've added to the solution, and thus maintaining a little bit of stability in the pH of the solution. So what we're going to do is kind of a long problem here, so this may take a little bit of time. So get something to to drink, some water or something, some chips, and just kind of follow along. Again, a buffer is prepared in this case by adding 1 mole of ammonia, and 0.1 moles of ammonia and 0.1 moles of ammonium chloride to enough water to form 1 liter of solution. So I'm going to keep the numbers as easy as possible so that we can see what's going on here. The first question we'd be asked is, well, what is the pH of this buffer solution? After that, we're going to take a look at the reaction that happens if we added nitric acid to this buffer. So again, how does the buffer react to that to help neutralize it? We'll look at the reaction, part C here, where it says write the complete ionic equation for the reaction that occurs if we add potassium hydroxide to the solution. And again, potassium hydroxide is a base. So again, how do we neutralize that base? And then we'll actually go through the math that's involved when you add 0.01 moles of HCl and the addition of 0.01 moles of NaOH. So we'll see how the buffer solution reacts to both the addition of acid and base. So first off, we have to figure out the pH of the solution before we've added anything else to it. So we're going to do our ice chart. This is an equilibrium. And you can actually choose either the Kb equation or the Ka equation. Since we're going to try to ultimately find out the pH, I think it's probably best to do the Ka equation. So we'll have NH4 plus, NH3, and the H3O plus here. So we were told again that we started with 0.1 moles of the ammonium chloride and 0.1 moles of the ammonia in 1 liter. So that gives us 0.1 molar solutions of each of these to start with, and 0 of the hydrogen ion. Change then is going to go to the right, so this will be minus x, plus x, plus x. Equilibrium, the hydronium ion will be x. The ammonia will be 0.10 minus x, plus x, and the ammonium ion 0.10 minus x. So our Ka, 5.7 times 10 to the negative 10th will be equal to, now of course the Ka is very small here, and because we already have some of the ammonia on the product side, x is going to be very small here. So we can go ahead and drop that from the calculations, the minus x and plus x. Of course we can't drop the x for the hydronium ion concentration, that's what we're trying to find. So look at this, we get x being equal to 5.7 times 10 to the minus 10th molar, which then if we do the pH calculation, gives us 9.24 for the pH of the buffered solution. So notice that the pH, in this case, with the concentration of the acid and the conjugate base the same, the pH is equal to the pKa. So if you take the negative log of the Ka value, you would get that. So what happens when we add a few drops of nitric acid to this mixture? Well, nitric acid is a strong acid, so it's going to ionize 100%. We don't really care about the nitrate ion, but we want to try to neutralize that hydrogen ion. So that's what we're trying to look at the reaction of. Well, what's going to neutralize the hydrogen? Our conjugate base. So our conjugate base is the ammonia, the NH3. And so that's going to form NH4 plus. So you see that additional hydrogen that's added will get neutralized by the conjugate base. Of course, we're forming more of the conjugate acid, so there's still going to be some increase, or excuse me, decrease in pH, but it'll get stabilized to some extent. In the second example, part C here, we're adding potassium hydroxide. So again, we have an alkali metal hydroxide, which is going to dissociate 100% in water, forming hydroxide ion. And then to neutralize that hydroxide ion, we're going to utilize the acid parts. Forming water and ammonia. So again, adding the hydroxide, we're going to neutralize that with the NH4 plus. We're going to form a little bit of this weak acid, but at least we don't have that, or excuse me, the weak base, NH3, but at least we don't have that strong OH minus in solution anymore that could drastically affect the pH. So what happens when we actually do add this base then? So here's the equation up there that we just had on the last page. Now we're going to do a slightly different table. This is a stoichiometry table. It's not equilibrium. So instead of doing ice, we're going to do if. Initial and final. Right, so not equilibrium, but final. We'll put up here the NH4 plus, the OH minus, and then on the other side of the equation we have the NH3. So the initial concentrations of this, these are going to be moles. So we have to switch to moles again here. So remember, the moles of the ammonium chloride we had at the beginning was 0.10 moles. The hydroxide ion that we're adding to this, if you recall from the beginning, that was 0.01 moles of hydroxide ion that was added. And we also had started with 0.10 moles of the ammonia. And what we're going to do is kind of artificial. I mean, obviously this thing gets in equilibrium and all this stuff kind of balances out, but we're going to kind of pretend that we're going to force everything over to one side. So I'm going to actually neutralize all of that base with the acid. So here's our base. I'm going to neutralize it with the acid here, and I'm going to neutralize all of it. So if this goes down to 0, that means the NH4 plus is going to also decrease, because that's what's neutralizing it. So this is going to go down to 0.09 moles. And it also means that the NH3, the ammonia, is going to go up by 0.01. So it would be 0.11 moles. We're going to divide each of these by our 1.0 liters of solution that we have. Now, in these problems, and it doesn't happen all the time, but the volume isn't going to change. We're just adding moles of this. So we aren't changing the volume. If we were to add solutions in which they would contribute to the volume, you'd have to take into account that there would be a new volume. So you have to add that volume of the solution to our existing volume. So what we end up with then is the NH4 will be 0.09 molar, and the NH3 plus 0.11 molar. Right? And then what we're going to do is we're going to take these to an equilibrium situation now then and run it through the equilibrium. So we've neutralized that OH minus, but that gives us new concentrations for the equilibrium. So we'll go ahead and fill those into our ice charts. Now we're back to equilibrium again. And again, you could use either the the base reaction or the acid reaction. Again, since we're doing the pH, I'm going to go ahead and use the acid reaction. From the last page we saw, remember that this was 0.09 molar. The ammonia went up 0.11 molar. And we artificially made the H3O plus concentration 0. So we're going to have a minus x, plus x, x, 0.11, plus x, 0.09, minus x. And then we do our equilibrium expression. So we've got the 5.7 times 10 to the negative 10th. Is equal to, again, the x is going to be negligible here, so we'll have 0.11 times x divided by 0.09. And we're not going to work out to where it's going to be exactly the same. It did change some, but you'll see that in this case the x ends up being equal to 4.66 times 10 to the minus 10th, which then gives us a pH value of 9.33. And remember, the pH of the buffer, the original solution, was 9.24. Okay, so we managed to keep that pH from changing too drastically from the addition of this base. What happens when we add the acid? Well, we're going to do the same thing. We're going to do a stoichiometry, not equilibrium. We're going to do if, right, initial and final. We're going to use the NH3 to neutralize that H plus ion that is added from the strong acid. In this case, we had nitric acid, or I believe it's hydrochloric acid. At any rate, we're going to go back to those original concentrations, 0.10 moles, sorry. We're going to do moles, again with the stoichiometry. 0.010 moles of the H plus, 0.100 moles of the NH4. May have too many significant figures there, but this is going to go down, so we're going to neutralize all of the H plus. So this is going to go to 0, which means the NH3, which neutralizing that, is going to go down by that much. So 0.09 moles of the NH3 And of course the NH4 is going to go up then to 0.11 moles. We'll do the same thing again. We'll divide by the 1.0 liters that we had. And our new starting concentrations then for the ammonia will be 0.09 molar, and new starting concentration for the ammonium ion, 0.11 molar. So we're ready to go to our molarity charts then, or our ice chart. Here again, I'll do the acid reaction. So I'll start with the NH4 plus, NH3, H3O plus. And the NH4 concentration, remember that was the one that, in the last one, let me see, the NH4 plus was the one that went up. So that went to a concentration of 0.11 molar. The ammonia went down, it neutralized the acid, so 0.09 molar, 0. So we're going to go up by x, that's x, up by x, 0.09 plus x, and down by x, 0.11 minus x, 5.7 times 10 to the negative 10th is equal to, again, we'll be dropping the x's from this. And here we get an x value equal to 6.97 times 10 to the negative 10th. And that's going to give us a pH of 9.17. And again, a reminder, our original buffer solution had a pH of 9.24. So again, we've managed to keep the pH from going down too drastically with the addition of the hydrogen ion. So I think we'll pause right there. We're going to come back and do another short segment on buffers that introduces the Henderson-Hasselbalch equation, and we'll kind of wrap up buffers.